Cooling towers. Cooling towers are ultra important for architects to understand and to get right. They take up a lot of space and have a lot of need for ventilation. It's important for an architect to plan at the concept stage the location of the cooling tower successfully. These images are cooling towers, but not the cooling towers we're used to seeing. These are obviously cooling towers of power stations. In our buildings, we use forced draft cooling towers. These are the two common types of cooling towers that we see in our buildings. There is cross-flow and counterflow. They are named with respect to how water crosses with air. In cross-flow, water is coming down vertical cooling pads and air is entering perpendicular to the water through the side of the cooling tower. Thus, being perpendicular to each other, air and water cross, hence the name cross-flow. In counterflow, the cooling pad is horizontally mounted. Water is sprayed onto the cooling pad and air is coming in through the bottom of the cooling tower and running parallel to the direction of water in the opposite direction. Thus, air and water are counter to each other, hence the name counterflow. The cooling tower receives condenser water from the chiller at a warm 35 degrees Celsius. This warm water is passed through the cooling pads of the cooling tower. Ambient air at Singapore design conditions of 31 degrees C dry bulb and 27 degrees C wet bulb passes through the cooling towers. As the air passes over the water droplets in the cooling pads, the water is experiencing evaporation and the water becomes cooler as it falls to the bottom basin. The 29 degrees condenser water is able to go back to the chiller to again reject heat from the condenser shell and tube heat exchanger. Older counterflow cooling towers were round in shape. You may see these on older buildings. Now let's focus more specifically on cross-flow cooling towers. Inside the cross-flow cooling tower, there is the hot water pipe, the fan, the hot water tank, the filler or the cooling pad, the eliminator, and the cold water basin. In the cut section, you can see more realistically what these pieces of equipment look like, including the access panel and the catwalks. And now for the counterflow cooling tower. The counterflow cooling tower has similar components. The filler though is horizontally mounted and the hot water pipe has nozzles. The eliminator is also mounted horizontal. The cold water basin is at the bottom. There is no hot water basin and there is a fan on top. The purpose of the eliminator is to prevent water droplets from being pulled out of the top of the cooling tower. Thus, the eliminator reduces the amount of water a cooling tower would use. Again, you can see the components in the cut section. And for the cut section of the round cross-flow cooling tower, you can see the same components. However, the nozzles will spin as water is pushed out of them. Thus, water is evenly distributed across the filler. So which is the right cooling tower to use? Both types of cooling towers have their pros and cons. Cross-flow are generally lower in height, where the counterflows are commonly quite tall. Counterflows are generally smaller in footprint. Crossflows have lower pump energy as they do not require to push water through nozzles. Counterflow have slightly higher transfer efficiency as water and air are passing counter to each other. Thus, it's a split decision and the cooling tower should be selected specifically for your project. Modular sizing or cells. To achieve the desired capacity of heat rejection, multiple cells are packaged together to add up to the desired size. The number of cells will depend on the cooling load and also cells are chosen based on redundancy requirements. As stated, the image on the right shows a full cell installation. Each cell has an individual fan. However, some cells can have twin or multiple fans, depending on the manufacturer and the model. So how to correctly design space for a cooling tower plant? This first installation seems very common, but it is wrong. The problems with this installation is the air on the facade side is blocked with a solid facade. On the other side is a solid core wall. These walls are seemingly too close. The top of the cooling tower has a trellis. In Singapore, the URA requires that trellis goes over the top of rooftop plants. However, this affects the performance of the cooling towers, and URA will allow for openings above cooling tower fans. It is not simply the performance of the cooling tower that we should be worried about, but also to ensure that the manufacturer's warranty is not compromised. Typically, all cooling towers will come with a CTI certification. This is a performance certification, and the manufacturer will ensure that the cooling tower performs to the requirements that it's specified, but on condition that the cooling tower is installed to the manufacturer's requirements. If not, the manufacturer will not honour the CTI certification and will not take responsibility for the performance of the cooling tower. The dimensions shown in this table are for this specific cooling tower and not general dimensions. However, we can see that the manufacturer has specific requirements that the walls must be a certain distance away from the air inlet to be sure that the right amount of air is able to get to the cooling tower. In this case, if 4 units of D12 type 14 foot wide are used, the required distance for a wall away from the cooling tower would be 4.8 meters. This distance is not small, and an architect needs to put consideration to this. Also note that the discharge of the cooling tower should not be blocked, and also adjacent structures should not be taller than the cooling tower, as prevailing winds would make the air short circuit. Having this knowledge, an architect can now plan for a cooling tower plant. The facade previously that was closed is now open with louvers. The core wall is pulled back away from the cooling tower. The discharge of the cooling tower is not blocked by trellis. While this is a satisfactory installation, some improvement can be made to improve the efficiency of the cooling tower. The discharge air will be creating a high pressure as it exits the top of the cooling tower. Underneath the trellis would be a low pressure. Air of high pressure will always want to go where the low pressure is. Because of this, there will be reentrainment of air and short cycling. The warm air off the top of the cooling tower will come back into the cooling tower plant in lieu of dry, cold, ambient air. By extending the discharge of the cooling tower to above the trellis, the high pressure and the low pressure are no longer beside each other, and cool air will be drawn into the cooling tower plant. As stated, the facade louver should be high net free area. Typically this should be above 80% free area, but this will be specific to your project. So now this is a good cooling tower plant design. Here are some examples of cooling towers. Let's discuss the issues with these installations. The lower left installation is quite well resolved architecturally. Louvers wrap around the cooling towers, allowing the cooling towers to breathe. However, if the discharge of the cooling tower was higher, this would improve the efficiency of the cooling tower. Also, it looks like the adjacent structure is close to the cooling tower intakes and is also higher than the cooling tower discharge. In the bottom right image, there is similar design issues. Again, it's best if the cooling tower discharge was higher. In the top left image, the facade has been removed as the air onto the cooling tower has been impeded. This is not uncommon, and it is often done because the cooling tower is not performing as it needs to. In the top right image, there is lots of space around the cooling tower, but the cooling tower is very much sunken in amongst the buildings. With the prevailing wind, the discharge air off the top of the cooling tower will likely be drawn back into the cooling tower. Cooling towers on rooftops are not uncommon, and architects should not be afraid of them. This image is obviously not of Singapore, and Singapore does have URA requirements for the static treatment of these spaces. These are some installations in Singapore. I'll clarify that the URA requirements are for the city and key areas surrounding the city. The top left installation is obviously very bad. It is sunken into the building, and the cooling tower cannot breathe well. Also, the discharge is blowing onto structure, which is creating mold and mildew issues. The top right image shows a trellis being installed over the top of the cooling tower. In this installation, the cooling tower performance was affected. The bottom left image shows lots of cooling towers squeezed together. The cooling towers cannot breathe and cannot be well maintained. The bottom right image is an example where holes have needed to be cut into the facade because the cooling towers have not been able to breathe. This installation was presented to me by BCA, and also the louvers along the side of the cooling tower enclosure were changed. Such modification can be very costly and impact the aesthetic of the building. This is another example in Singapore, and I'll explain how this was modified to fix the issues. The cooling towers were sunken too low, and also multiple rows, meaning air in was coming past the discharge and air was being short-cycled. To fix the issue, the cooling towers were lifted higher. By lifting the cooling towers higher, Air in was able to come in through the side louvers and was no longer coming in through the top. Also, the discharge was able to blow free and out of the building. Here's an example of a good installation. This is Pi Labour Quarter by DPA. The cooling towers are put below a trellis and the discharge is raised high above the trellis so that there is no re-entrainment of air. Holes are cut above the cooling tower fan, which were coordinated with URA. This image is taken directly above the building, so we can look easily through the trellis. However, from neighbouring buildings, the aesthetic is good with the trellis blocking view into the plant. This installation did have a challenge. NEA has strict requirements on the separation between cooling towers and occupied spaces. Public should be kept more than 5 meters away from cooling towers. The reason for this strict requirement is because of Legionella, which is a bacteria that can grow in cooling towers. Cooling towers do have treatment systems which try to fight against the growth of Legionella. However, these are not foolproof. Legionella causes Legionnaire's disease. Legionnaire's disease is a killer and people do die every year of Legionella's disease, with one of the main causes being cooling towers. Thus, at Pi Labour Quarter, a barrier needed to be built to separate the people from the cooling tower. Because of this, the air intake to the cooling tower was impeded, but it was able to be negotiated with the manufacturer that sufficient louvers could be provided on this side of the cooling tower at a slightly elevated height. If done right, cooling towers can work well into the building shape and form. Marina Bay Sands is a good example. The trellis has openings above the cooling towers, so we can see them in this image. A kinetic facade wraps around the cooling towers. This is both beautiful and operationally suitable. Great consideration has been given to the placement of the cooling towers, and this ties into the building mass which is going between the towers. I give Marina Bay Sands high accolade for how the cooling towers have been integrated into the architecture. To finish off on cooling towers, I'd like to clarify that these images shown of cooling towers for power stations are similar to the cooling towers for our buildings. Air comes into the cooling tower through the bottom. There's trellises as can be seen on the middle image. Filler runs horizontal and hot water pipe is spraying water onto the filler. However, there is no fan in these type of cooling towers. This is a natural draft